Uh, so welcome everybody. Today I'm going to talk about some work that we've been doing within NetApp for the past several years. This presentation, actually, I have a collaborator, Samya, who's a data scientist. He's in Bangalore though, so he's probably fast asleep right now. So my talk is actually in 4 parts. First, I'm going to give you a little context for this talk. What is Active IQ? What do we do with it? Some of the challenges we have with machine learning. And then a high-level description of our machine learning platform. And then finally, an interesting open problem that we're working on, where we'd love to get your feedback and your input. So Active IQ, so for those of you that don't know, right, NetApp is a pretty large data storage company. We sell all kinds of storage products, became famous years ago for building very high performance NFS systems. And since then, we have expanded and we have a portfolio of storage products, including some software-defined products that run in the cloud. So like, for example, if you go to any of the public clouds and you want NFS as a service, you can use something called the Cloud Volume Service. So all of these products, whether they're software, hardware combination, they all send telemetry data to us every single day. And we get approximately 10 trillion data points per month. That's how much we see today. That number is doubling, I'd say, roughly every 18 months. So it's a pretty significant amount of data. We take all of this data and we run it through our data engineering and machine learning platforms. In aggregate, we have roughly about 20 petabytes of data today, 5 petabytes of what I'd call hot data that we look at quite a bit, and 15 petabytes of archival data. And we mine all of this to produce insights. So this is the application called Active IQ, which is our digital advisor that helps our customers maintain their storage systems, optimize the performance of it, and so on. And so there's 3 flavors of it. You can get it as a web application, mobile application, or increasingly customers just consume the insights as APIs. Now, what is the problem that Active IQ is trying to solve? So here's a pictorial view of the day, it's what a storage administrator goes through on a regular basis. And in fact, this is true of any system administrator. So somebody somewhere in the organization wants to run an application. Let's say they want to deploy MongoDB. They come to a storage admin and say, I want to deploy MongoDB, I need some space, right? It's a lot more complicated than that. It's not just space. You may need to have certain performance requirements and various other issues. And so now the storage admin has to decide where to provision this space, how to configure it, and they have to monitor it to make sure that it meets the SLAs of the application. And of course, periodically things go wrong, stuff fails. And so they have to take care of all of these things. And Active IQ is built as a software digital advisor to enable the system admin or the storage admin to get better outcomes, to do a better job. And the fundamental problem is this. See, if you think about how a storage administrator does a really great job, it's really 2 things, right? One is they have to go read documentation, which could be tech reports, maybe stuff on Reddit, Stack Overflow, or very often it's just experience. There's a lot of stuff that you learn just by experience. And it's a combination of these 2 things that make a storage administrator very good at his or her job. Okay. Now the problem is there's a lot of information out there, right? NetApp itself has thousands of pages of tech reports for all kinds of applications. Then there's Stack Overflow, there's Reddit, there's so many forums where there's information. It's simply impossible for a human being to read all of that and understand what's going on. And well, anyway, these days, nobody seems to want to read anything. And also, you can't wait forever to people to get the right experience to do all of this. So how do we simplify all of this? So our vision is really, the equivalent of a self-driving car. We want to make the whole process of deploying storage, managing it, maintaining it, upgrading it, everything self-drive, right? This would be the ideal world for us and for our customers. And for a variety of reasons, it's very hard to get to this state, right? But we're making progress towards it. So we already use So like I said, this is our big picture vision. We're definitely not there yet, but we already use machine learning in a variety of ways to try and automate some of these things. So one of the places where we use, actually this is the whole list of things that we do with machine learning effectively today. I'm going to cover only the first three because some of these other things are very storage specific and maybe difficult to understand. But a very basic thing, right? Very simple thing is just predicting when you're going to run out of space and taking some actions based on that. And that's something we can do effectively with machine learning today. The second thing that we've done fairly effectively is we get these 10 trillion data points a month from tens of thousands of customers around the world. So not only can we observe what actions they've taken, but we can also learn the consequences of those actions. So what actions they've taken, we can essentially learn from things like logs that come in the telemetry data. But understanding the consequences of those actions is where we use machine learning. And then we can infer from these actions and consequences and essentially create best practices that we can then present back to the customers to improve their outcomes. Third fairly straightforward thing we do with all the data we have is, we have a chatbot called Elio that's available on our customer support site. And you can ask it basic questions like, how do I configure a volume? How do I back it up and things like that? And it can extract that information from documents. So these are all, I'd say, fairly straightforward things. You'll see variations of this in the industry. And then we do a few more complex things. But what's the problem with all of this, right? What's the challenge with doing all of this? One of the big problems is, there's a really long list of machine learning projects that both we're doing and we have planned. And what ends up happening is that if you don't have the right platform to do all of this, you have lots of custom deployments of your machine learning models. And that's what was going on initially. The second thing is we had lots and lots of custom models for different use cases. So there was a lot of duplication of code. There was enormous duplication of different facets of the training data. The other problem we had is we were doing all of this in the public cloud, and the costs were just completely spiraling out of control. Now, this may not be a problem for some companies, but for us, it became a very significant number. The fourth problem we had is our feature store was essentially Hive. And that's just too slow to do interactive analytics. So what very often happens before we build a machine learning model, we will do a lot of interactive analysis, look at the data, understand whether we have valid data. Is there really hope of doing something useful with it? And so we do a lot of interactive analytics, and Hive was just too slow for that. The last part that I'm not going to talk about, because that's a whole talk in itself, has to do with data governance and regulatory constraints. So what happens for a large enterprise company like ourselves is we have customers that are the governments of countries, and also customers that are in different countries. And many countries, especially governments, are imposing a lot of constraints on where you can store telemetry data and who can access that data and so on. And handling all of this, adding all of this to the feature store was a fairly complicated thing to do. Okay? But like I said, I'm not going to cover it in this particular talk. So to solve these problems, we essentially took 4 steps. The first step we did is we decided to build a high-performance feature store. We decided to essentially get rid of our Hive data store, and we partnered with a startup called Iguazio. Now, Iguazio does, I'd say, 3 things for us. The first is they have an open source serverless library called Nucleo. So all our data prep code today are essentially serverless functions. And we found that for the vast majority of our programmers, this was actually a very convenient way to do things, right? Data prep fits very nicely with functions as a service or serverless. The second thing that Iguazio does for us is they integrate with our storage. So most of the serverless things out there, they typically only work with object storage. But Equasio did a bunch of clever things so they can actually handle something like a mount point, which is our NFS storage. And then the real reason we picked them is they have an extremely high performance database. They call it a multi-model database. It's capable of handling time series data. It's capable of handling, regular key value data, all on the same data store, highly compressed. So today we actually process about 90 billion performance counters in under 200 milliseconds in this feature store. Okay, so these are the three reasons why we picked this, and this feature store is what then feeds our machine learning jobs. So that's the first part. The second part is we looked at all the problems we were working on, right? Like predicting disk failures ahead of time, predicting when a network card is going to fail, predicting when you're going to run out of space. Lots and lots of these problems. We looked at all of them, and then we had an aha moment when we realized that really all of these problems are just variations of time series problems. So we said, rather than building so many custom models for all these different machine learning problems, what if we built a generic time series engine that has 5 primitives in it? So given any time series data, it can do forecasts, it can detect anomalies, it can detect what are the correlations between these time series. So that's very useful. For example, like let's say you're predicting that a storage system is going to fail or that it's going to become very slow. And you want to answer the question, why is it going to become slow? You can look at correlations across time series and say, I think it's because of, blah reason. Fourth abstraction we have is the notion of change points. So for example, you may notice that your storage system is got very low latency, it's under 5 milliseconds, and then suddenly shot up to 100 milliseconds and it's staying there. So something has changed. And the question is, what has changed and what else is it correlated with? Right? And the last thing is a little complex to do. We call it causal analysis, where we try to, when we get all these different time series data, we try to infer what caused what. So we built this generic engine. We gave it we're not too good at naming, so we called it the zero ops engine. It doesn't really mean anything. But we take all of this data that's in our feature store. So what's in our feature store? It's things like logs, right? Our storage system logs. Think of it, like in the Linux world, it would be the equivalent of your Linux logs. Or performance counters, or significant events that have occurred. So all of these things we extract from our feature store. We convert everything to numbers, a vector of numbers. We pass it to the zero ops engine that can then produce these 5 primitives, model these 5 primitives, and then we can reconvert that into domain-specific predictions. And so this has been a huge boon for us, a really small team that is building this core engine. Now, the third thing, so I spoke about 2 things. I spoke about a feature store that's high performance. I spoke about essentially recasting all our machine learning problems into a series of time series models. So we don't have to build too many models, custom models. The third thing is, how do we manage all of this and deploy this at scale? So today we have about 100 million time series that we would potentially have to build models for. Okay, that number is going to go up to about 500 million fairly soon. So it's a very, very large number of time series. And it turns out that you have to tweak the model for each time series, depending on the nature of the time series. For example, if it is something to do with performance, it's one kind of model. If it's something to do with capacity, it's a different kind of model, and so on. And we needed an efficient way to manage all of this. So essentially, we turned to MLflow to do this. So you see this is a very detailed picture, but I'm just going to focus on the right side. So we get all this time series data in streaming fashion from our feature store. And what we do is we have a training module, which you see at the bottom, which is where we will try sometimes an ensemble of models. Okay. And we then store the results using MLflow. So our model tuning parameters, our evaluation metrics, all of this are in MLflow's tracking data store. And the model itself we store using, so MLflow has this notion of flavors. And so we use the Python function flavor. In other words, no matter what libraries we're using for training, whether it's PyTorch or scikit-learn, we ultimately store that using this Python function flavor in the MLflow tracking artifact store. And then what happens when we need to make a prediction, right? So let's say we've built these models across all the gazillion storage volumes that we see across all our customers. And let's say we built a simple prediction to predict when you're going to run out of space. The moment someone comes and asks us that question, that data arrives at our inference module, and then we use MLflow's models primitive to go, get the right Python function, the best Python function to make the prediction. So using MLflow has really, helped manage this process very well for us. But here's a problem we had even with this. The problem is that when you're trying to do this, for 100 million time series like we are, or like I said, we're going to get to 500 million, within a year. At scale, this is an extremely expensive problem. And so why is it expensive? You can use simple statistical techniques to do forecasts, okay? But it turns out that you have to do a lot of work to fine-tune them. There's a lot of handcrafting that's involved. And clearly you can't do this for millions of time series. The other option is to use things like recurrent neural networks that are actually pretty good at generalizing these forecasts, regardless of the time series, but they take a lot of time to train. And so we looked at one particular time series that we have internally, having to do with storage latency. There's a particularly odd-looking time series. And we tried a bunch of forecasting models. And what we found was that we got actually the lowest error rate using an RNN, but it took an hour to train, right? So it generalizes well, but takes a long time. And now if I have to do this over 100 million time series, or half or whatever, it's a really long time. And doing this in the cloud would have essentially bankrupted us, right? Just wasn't feasible at our scale. So the fourth thing we did is we split up our training and inference so that training happens on premises because it's constant in nature. So we take our feature store, which I told you is the Iguazio database, and we feed that into a product that NetApp sells in partnership with NVIDIA. It's essentially a GPU cluster. So we have an 8-node GPU cluster attached to very high-speed SSD storage. And it's a one-time setup thing, one-time cost, and then we use this constantly. And we found that this reduced our cost of operation anywhere from 3x to 10x, depending on what we were doing. But for inference, because inference is not constant in nature, right? It happens on demand. We do that in the cloud. So we do our training on premises. We push those models to MLflow that's in the cloud. We use Amazon, but technically we could use any cloud. And then all our inference runs there on demand in containers. So those are the 4 steps we took to sort of optimize and simplify what we're doing with machine learning. Now, I want to talk about something that we're planning to do in future. Okay, so I told you that we have solved a bunch of problems with machine learning. We have simplified it by essentially recasting those problems as time series problems. But ultimately, everything we're doing today can predict that a problem is going to occur. The really difficult part, if you want to get to true self-driving, is to know how to fix the problem, right? And this is really, really hard to do. So how does a human being learn how to fix the problem? Well, they can go read some tech reports that may have the answers. Oftentimes, there are support tickets that would have the answers. Or you might do a Google search and look up something on Stack Overflow. So the point is the information to solve a lot of these difficult problems, as long as you can make an accurate prediction that a problem is going to occur, the knowledge to solve these problems exists somewhere. The problem is it's buried in a lot of documentation. Some of this documentation is highly structured, like a tech report, but some of it, like Stack Overflow, is very unstructured. And the really difficult problem we're working on right now is, how do I take all those sources of potential sources of answers and extract some best practices or rules, or even a solution, and code that up, for example, in something like an Ansible script. So the magic sauce for us would be that we're able to predict, for example, that your storage system is going to become very slow. And we're somehow able to gather all this information from documentation and create a script on the fly that the customer can deploy, that then goes and solves the problem, right? Like I said, this is really hard for us to do. We've actually started by doing some collaborative research with universities. And if you all are interested in looking at this stuff, we just published a paper. So this was work done by one of our summer interns from UC San Diego. And he did some really clever work, which is he's able to look at all our tech reports and extract the best practices using some NLP techniques and statistical techniques, right? And then we can then tell the customer, here's how you got to re-optimize your storage setup. So this was published at Usenix last month, okay? So in summary, we had 4 challenges with what we were doing with machine learning. We had too many custom models, lots of interesting projects, but way too many models. Our cloud costs were spiraling out of control. And we had a really slow feature store that slowed down the pace with which we could do some prototyping ahead of time. So we took 4 steps. We built a high-performance feature store in partnership with a company called Iguazio. We abstracted, I'd say, about 80% of our machine learning problems into generalized models that are time series based and that have 5 primitives attached to them. We use MLflow to manage all our model runs and serve models. That's worked out very well. I should point out, we're also looking at something called Selden Core as we migrate some of this to a Kubernetes environment. And the last thing is to greatly reduce the cost. We do all our training on premises because that's very cost effective. It runs very often. And we do all the inference on demand in the cloud. Okay. With that, I'm going to end the talk and see if there's any questions.
Thank you, Shankar. So there are 3 questions on the Q&A. Maybe you could take those in turn. If you'd like to answer them live, that would be great.
Sure. So first question is, do you consider SSD SPART metrics as part of your analysis and predictions? Yes, we do, but what we do is way, way more complex than that. Because, I mean, this is going into the details of storage, but we figured out over the years that storage fails in so many bizarre ways that we have a lot of internal metrics that we gather as well. So it's a lot more than the smart metrics themselves. And if you go look online, we've written a bunch of papers in the research community about all of this. What are the data points? The second question was, what are the data points you consider for fine-tuning your models? So I'm not entirely sure how to answer that question or what the question's about. I mean, so it depends. Ultimately, if you're talking about, so one thing we do, of course, is look at the accuracy rate, the false positive rate, and so on. And it really depends on what problem we're trying to solve. See, for example, if I'm trying to predict if your storage system is going to fail, it's okay if I miss some instances where it would have failed, because you're no worse off than if I didn't make the prediction. But you certainly don't want to predict incorrectly, right? That's going to frustrate your customer. There are other times, like, for example, you're predicting capacity growth where you can be off by quite a bit. So the accuracy that you need to achieve varies greatly by the domain and the problem you're trying to solve. And so, that's really what we look at to decide how to fine tune our models, if that's what you meant. And if I didn't answer your question, feel free to just elaborate on that. The third question was, what criteria do you apply when splitting the time series data for training and testing the models? Again, it really depends. See, I'll give you an example. So let's say you're trying to predict storage capacity growth. And let's say, your storage was unused for a long time and suddenly it's, going up on a linear curve, 45-degree curve. If you use all the points that you have, let's say you have a year's worth of data and for 6 months there was no growth and 6 months there's a lot of growth. Depending on the model you use, and if you use all the data, you're going to have a really bad forecast. You really have to know that a significant change occurred and then use only the data after the change to make that forecast. So again, this is unfortunately very domain and context specific. While I did tell you that we're trying to build this sort of generic time series engine, which we have built, the reality is there's still a fair amount of work that we need to do that's very context sensitive. Okay. Then the last question is, I'm curious about how the feature store is optimized for different kinds of downstream jobs. Yeah. So yeah, that's a great question. One of the really nice things about this Iguazio multi-model data store, and you can go online and read more about it. It's really clever. They essentially we store everything essentially as time series data, but you can look at it multiple different ways. You can look at it as a generic key value store. You can look at it in time series fashion. You can look at it multiple different ways. So that has really helped us. Okay, we didn't have to create multiple different databases for different reasons. And like I said, there's a lot more about this online that you can look at. The other fundamental thing that we do is we try and convert everything we store into numbers. So like, let's say you have a log of messages. We convert that into a vector of numbers. And that's, again, a very hard problem to solve, right? And there's lots of papers written about that. But that's essentially what simplifies the picture for us. We try not to store text data in and of itself. We try to structure it a little bit and store everything as vectors of numbers. What are the next steps that NetApp is looking at to take in its ML implementation plan? Well, we are in the process of deploying all of this as part of ActiveIQ. The stuff that I showed you is also used today to manage our data pipelines themselves. So all that infrastructure we have with Iguazio, these serverless functions, the various databases, that entire pipeline is also managed by these machine learning models. So it's a little bit of a recursive thing, right? And that's actually been very effective. So we can quickly determine that some part of our pipeline is not working, or there's data that's missing, all these sorts of things. Okay. So yeah, some portions of it are already deployed, both for ActiveIQ and managing our infrastructure. And obviously we're doing more with this right now. Yep. So I think that's the list of questions.
Thank you very much, Shankar. I actually had a quick question as well.
Sure.
I was kind of trying to understand the sort of the connection between the serverless operating mode for data prep and the scale that you have. I can certainly see the convenience of serverless, but I'm not quite sure. I mean, at the volumes of data that you have, why is it that not a big batch job, is what you need? I'm missing something there.
I see what you're saying. We have a rule for most of the data that we get. Yeah, good question. In fact, our old architecture was batch oriented. So data would arrive, we store it in 10-minute buckets. And then we had a bunch of Spark jobs, or in the old days, MapReduce jobs that would process that. So what's happened is we need to, there's two reasons why we have these serverless functions. And one of the big reasons is the moment data arrives, we need to infer and make a prediction pretty much instantly. Like we have an SLA that if a new piece of telemetry arrives, and within under 2 minutes, we will open a case if we can predict that there's going to be a case.
Okay.
Yeah.
I see. Okay, makes sense. So you're sort of in some ways processing the data as it arrives, as opposed to doing like a
Yeah,
massive batch data prep sometime later.
that's right. That's right.
Okay.
Yeah, there's a separate part of the ecosystem which I don't have this in this picture, where we still have some bad jobs running.
I see.
Yeah.
I see. Makes sense. And just one curious, because I mean, I'm not really surprised that cloud is, impractical for you at your scale from a cost perspective. I'm curious when you got there, as in, for people who don't have a trillion data points, are they
Yeah.
going to find cloud prohibitive at 10,000, 20,000, a million, a billion? Where would it be before the cloud becomes prohibitive?
So we got there very fast.
Okay.
Very fast. I remember we started a project, and it had some budget of X per month.
Okay.
And within 3 months we were 12X.
Ah, I see.
Yeah. And my boss called me up and said, please shut it down. So yeah.
Okay, I see. Makes sense. No, that's actually very helpful, because I think we've heard that, at least I've heard that from a number of people, right? And
yeah.
I was curious kind of where the point was for you, the breaking point.
Yeah. One thing I do want to mention about serverless functions. So we rewrote some of our existing Spark jobs as these Python serverless functions. And when we were first doing this, people said, oh, is this really a smart idea? Why are we doing this? It turned out it was fantastic. So we have 6x fewer lines of code. It turns out that thinking of your pipeline as a set of composable functions actually works out beautifully.
So it's just to make sure I understand, you put a Spark job inside a serverless function?
No. So we had existing, before we got to this architecture, we used to have a pipeline that had Spark streaming.
Okay.
Okay. But we took that code, that Spark streaming code, and we took all the logic out of it and rewrote that as simple serverless functions.
Oh, I see.
Yeah.
Makes sense.
So we had that Spark streaming code in Scala, and then we rewrote it as Python, these serverless functions, using this thing called Nucleo, which is part of Iguazio. And like I said, when we initially did that, people questioned, is this really a smart idea? But it turned out to be amazing for us. It's much less code. It's much easier to understand and manage. It's actually very fast. It's really fast.
I see. Awesome.
Yeah.
There's one more question, by the way, from the audience. It's the last question on the list.
Yep. Oh, yeah. Let me look.
It's from Mark. Yeah.
Oh, for feature store, did you consider Cassandra? Aha. Good question. So we did have Cassandra, and didn't work out well for us. So we actually retired Cassandra with this Iguazio database. There are a lot of issues with Cassandra. Managing it on premises was a real pain. We had lots of performance problems, and maybe we weren't doing such a good job of it. I'm not really sure. And then we also wanted this multi-model aspect of Iguazio, right? So we didn't like so Cassandra has its own query language called CQL. Whereas the nice thing with this Iguazio database is you can use, standard, pandas, data frames, basic abstractions that you're used to, and connect with it. So it was much easier for our data scientists.
I see.
Yeah.
So thank you very much, Shankar. And anybody else, I think we'll take a couple of minutes. And if anyone else has any questions, please do put your questions on the Q&A.
One more question, I think.
There's a thank you message from.
Oh, I see. Okay.
Yeah. So yeah, we'll just ask for one more minute and then close the talk. So did you consider, just one more question, did you consider sort of the Nucleo layer and the feature store as independent things, or did the presence of, okay, so they were really independent? As
completely independent. Yeah, you can deploy, in effect, I think you can deploy one without the other. And we actually do that for a separate thing that's not shown here.
I see. So, okay, makes sense.
Yeah.
Okay, so I think that's it. Thank you so much, Shankar. This was a really cool talk.
Cool. Thank you. Thank you, Nisha.
Thank you.
Take care.
Thank you, everyone. Thanks to the audience. The next talk will be starting in about 4